Now we are going to start our lecture number 5. And our plan for today is this one here. We are going to just position my class notes here. We're going to do some examples of calculation of the potential function directly from the integral expression we derived in lecture number 4. Then we are going to go to define the energy of an electrostatic system in vacuum, a set of charges in vacuum, what would be the energy to maintaining those charges together, energy of the system. Then we can conclude that with Maxwell's equations for the particular case of electrostatics in vacuum, okay? And then we have, as those are differential equations, we need to use boundary conditions, because if you have different regions, let's say, we would have to employ boundary conditions. That will be clearer when we move on to material media. When we have different material media, then we have different solutions that have to be matched at the boundary of the interface between those two material media. But first, let's conclude that small portion of lecture number 4 that we left open in the last time. Okay, I'm going to move on to the final part of lecture number 4. We just derived in the last part, we derived when we demonstrated, right, that the E field, as given by this integral expression, and we did that. I mean, I hope you have, you guys have worked out this identity here, right? The difference vector divided by the third power of the magnitude of this difference vector equals minus gradient of the inverse function when it is applied, when the derivative is applied to x, or plus nabla prime when the derivative, which is labeled here as nabla prime, is applied to the coordinates of x prime. So we showed by doing that the E field could be written as the minus gradient of a potential function, and the function is simply this scalar integral over the volume of charges, right? It has a very simple expression. This is the amount of charge, the differential charge in volume V prime, dq, divided by the constant that we have in our formulation, 4 pi epsilon 0, and the magnitude of the difference vector, difference between, I need my, sorry, every time I forget this, my draft, my notes, where is it? Where is it? Sorry. Let's forget that. I think it's this one. No. Or here. I think it's this one, yeah. We have the, just reminding you guys, so you have x prime is the location of the volume in which the charge density is rho x prime, and x is the position where you determine the potential function. So we have essentially potential at x, right, at the position, at the point observation point, equals a volume integral. I mean, this occupies a volume, right? It's charged I mean, let's say that the total charge is Q, but the charge is distributed with a density rho. So this goes like this: rho of x prime divided by 4 pi epsilon 0 magnitude of x minus x prime. So we showed that. We mentioned that the unit of this is volts. So if you look at the definition here, so the volt, which is the unit of potential, is charge. Okay, let's say it's unit of charge divided by epsilon 0 is farad per meter, right? Farad per length, let's say, times length. So the magnitude here is length. So you have you cancel that. So it's unit charge per farad. Okay, so this is the volt. Okay, 1 volt equals to 1 coulomb per farad. Alternatively, 1 farad equals 1 coulomb per volt. Okay, so so we have also, I mean, we demonstrate that, and also demonstrate that the E field is given by minus gradient of the potential. So let's just look a little further on the units here. Let's recall that this is force per unit of charge, which is Newton per coulomb, right? So E field is measured also in Newton per coulomb, which is equals to volts per meter, which from the definition there, right? So the volt, in fact, is what? Is Newton meter per coulomb, alternative, right? Coulomb per farad, but also this is joules. So 1 volt equals to 1 joule per coulomb, okay? So we have all those units. We have to look around. So we stop at that. Then what we didn't do, I mean, and also we mentioned, let's not forget, that the potential can be arbitrary to a constant value, okay? So I can add or subtract the constant to the potential without affecting the E field. So in general, in field theory, potential functions are those functions that are intermediate between the original problem and the final quantity that you want to determine. So in this problem here, is given, let's say that you give the source, I mean the charge distribution, and your aim is to determine the E field, okay? So when you talk about potential functions, so have source and final quantity is field, let's say. So you can go directly, as we did, an integral expression, or you can go through an intermediate step when you determine this auxiliary function called the potential. So you go from source to the potential, then from potential to the field, right? That's what we are doing here. There are scalar potentials and vector potentials. Some potential functions have physical meaning, others don't. So the scalar potential has a physical meaning that we are going to show you in a couple of seconds, okay? But there are potential functions, so intermediate functions, that might not have a physical meaning, a priori physical meaning. So, let's look at the potential function in the way it is. Let's look at the work. Assume that we have a point charge. We have a field region here, okay? Permeated by an E field. This E field is created by a charge distribution somewhere, okay? Then you have a point charge very far away from this E field, doesn't feel the influence of the field. Then you bring that charge towards a final position along a path, okay, a curve. So at any point, the E field, I mean, you imagine that an external agent is giving energy to this particle or to this point charge to bring it to the final point. But it's doing that in a process that is a quasi-static process in which the external agent equilibrates, okay, it balances the electric force that is acting on the charge at every point in the path. Okay, so in this figure here, you can see that at some point you have this charge. So the external agent is applying a force F external, which equilibrates perfectly the electric force. So it does that until it gets to the final point, let's say, which the final point is this point here. So there is some work that is being done by the external agent, and this work that is being done is being given to the particle, to the point charge. So at the end of the process, the charge is going to be with some energy, because if the agent lets, just let it go, the charge is going to be accelerated toward the distribution or away from it, right? So that's the energy of the particle in the external field. So you had to calculate this energy given by the external agent to bring the particle to the final position. That's how we do that. So the energy given by the external agent is simply the work done by the agent, which is the line integral of fx dot dl to move between points A and B. That would be the integral. But in our case, we want to calculate the energy, which is going to be the energy at point P, okay? Because we are going to bring from infinitely distant position to the final position, right? So we are going to do that. And what happens? Let's assume that we are so far at the initial point that there's no energy of the particle. You can add a constant if you want. You know that's not going to make any difference. But I mean, let's say that this energy of the particle far away is 0. So assuming that the external agent is equilibrating the E field, so he's going to apply a force that opposes the electric field force. So that's going to be minus integral to point P of F electric force, dl, right? And we know that the force that a point charge Q feels on an E field E is going to be Q times E, which is the electric force. So we plug that in here. It's going to be minus Q integral I'm not saying what is the path. I'm just saying through any path. I'm going through any path from point very large distance to final point P, not specifying to what is the curve that this path comprises. So, but I mean, anyhow, we know that E equals minus gradient of potential function. What potential function? Well, the potential function that describes this field E, right? So we have the energy, this comes from here, right? The energy at point P equals to, this minus cancels these ones, you're going to be Q well, by definition, this is nabla, if you make a dot product between nabla and the L, well, the L has a tangent vector, right? Times the L dot nabla. So this is the L T dot nabla. Well, T dot nabla by definition is the projection of the nabla operator along the tangent direction. But here, the projection is simply the derivative relative to the differential length, the L. So this is, so this in fact is Q the L defy the L, right? So this is the differential of phi of the potential function. So here we have that the integral, we will rewrite here, from infinite to P or Q, the L defy the L. Now, as I make change in variables, instead of going from coordinate space to potential space, so I've made a change of variables. The new variable, integration variable, is the potential itself. So this is going to be equals to the potential at the infinity, the lower limit of integration, potential at P, and there's a Q here, I forgot, the phi, right? So this is going to be the energy at P is going to be Q potential at point P minus potential at phi infinity. If I use by convention that the potential at infinity is 0, might not be 0, might be a constant. So we have, you know, the final results that the energy so I'm going to say that the energy at point P is going to be the energy of the charge Q, which is the value of the charge and times the potential that the charge feels at point P, right? This potential at point P is the potential at the location of a charge. So there's no charge, so the potential has a value at a given point P. You pick a charge at that point, so the energy of the charge is going to be the product of the charge times the potential at this point. Very simple result, right? So at the same time, the potential has this physical meaning. Is the energy of a charge, test charge, divided by the charge, right? So energy in joules per coulomb, as we mentioned before. Okay. Well, this is the physical meaning. So energy, potential energy and potential function are very similar, right? Energy at a point in space, you just put a test charge in that point, calculate the energy of this test charge and divide by the magnitude of this test charge. I mean, by the value of this test charge. So you're going to have an energy, right? Let's say if the charge is positive, the potential has the same sign, right? Same sign as the energy. If the charge is negative, the potential has an opposite sign of the energy. Okay? Okay. Well, there's another property which is going to give us a second integral equation for the field, for the E field. The first integral equation was Gauss's law, right? We have the flux through a closed surface equals the enclosed charge. That's one integral relation. There's a second integral relation that comes out from this property, which is what we have here. Let's see. You see, from going back to the relationship between field and potential, we can calculate the potential difference between 2 points I just made a demonstration, right? This is going to be minus integral from A to B, right? Of the minus is minus nabla of phi. Let me rewrite this like this. I'm sorry, it's not minus nabla, it's plus nabla, right? Sorry about that. Equals to the L nabla of phi from A to B, right? So that's the potential difference between 2 points, phi B minus phi A. So if I use this, this is minus E, right? So I have this simple relationship here. Okay? But you see that, I mean, this doesn't depend on the path. I can go from A to B through any path, and the result is always the same, because those functions, as I just showed you, a potential function giving a reference, this integral is unique, has only is single valued. So in giving a reference to the potential at a given point in space has only one value. Okay? So it means that this has one single value, and this has a single value, and this is always constant, right? Given points A and B, this delta phi, potential difference between of the potential values between two different points, is always constant, because the potential is unique at any point in space. So it means that this integral doesn't depend on the path on going from A to B. You can go through any path, right? That's the property of a conservative field. Because if I go from A to B like this, and go, so let's say through CAB, let's call this one CAB. So integral from through CAB of EDL is equal to integral through CAB prime, right? But going through CAB prime is the opposite of going from B to A, which is, let's call CBA prime, okay? So this integral here, CAB prime, equals to minus integral from CBA prime of EDL. So if I do this, so if CAB plus CBA prime equals to 0. So this is nothing less than the circulation, right? This is the closed path. So if I close the path, go from A to B, and close the path going from B to A, so the circulation of the field equals to 0. So that's the property that we have from the relation E equals minus nabla phi. Okay? So that's a conservative field. That's one equation, one integral equation. That's a direct consequence of the fact that the field can be obtained from the gradient of a scalar function. This is because the field is central field, right? And the field depends only on the distance. A point charge doesn't have, would not need to have a field dependence that 1 over the square of the distance. Only the fact that the field depends on the distance, whatever it is the dependence, and the fact that the field is radial. That gives a conservative field. Any field that depends only on the distance and is radial, okay, any field of this form has this property, right? A fictitious field, a field called field, which is f of r, AR, has this property. Field dl equals 0. Right? Because this thing can be shown to be the minus gradient of a scalar function. It's going to have that property. Right? So that's what we have for the potential function. Let's do some calculation examples for the potential function. So that's our lecture for today. That was the conclusion for our last lecture, right? Let's see if I missed something here. Okay, so that's what we have. The final property of the last lecture is that the circulation of the E field is 0. So let's do some calculations. We're going to explore the properties of Dirac's delta function to do those calculations. For different distributions in space, we are going to always represent those distributions, those charge distributions, as volumetric distributions. So we're going to always use a volume integral. Of course, we can reduce that integral to surface integral in some cases, to line integral in others, but we are going to explore the Dirac's delta function, and every time we are going to calculate the potential as an intermediate step to get the field, we are going to use Dirac's delta functions. So let's do a very simple example. What's the potential of a simple point charge, right? The point charge is located at point x0. We want to determine the potential at point x. So the density of a point charge using Dirac's delta function is given by this. The location is x0, so the delta function peaks, this blows up right at x0. So that's the definition of the potential function. Okay, so is this volume integral of a volume density, charge density, divided by 4 pi epsilon 0. Where is the integral? Integral is made in the whole space, because we want to pick all the charges. Okay, but we have only one single point charge, right? So if we plug the expression for the charge density, okay, this q goes out of the integral, 4 pi epsilon 0 2 go out. So we're going to have the simple integral of a dv prime, a function of x prime, and a delta function of x prime minus x0. Let's just remind you that the property of the delta function, right? The integral of f of x prime, delta of x prime minus x0 dv prime equals to f of x0 if x0 is inside what? Inside the integration volume, right? Or is 0 if x0 is outside. right? But our integral is on the whole space, so it's going to be always fx0. In the case, fx prime equals to 1 divided by magnitude of x prime minus x0. So sorry about that. Sorry about that. It's not that. It's fx minus x prime. X minus x prime. That's the function. X is a constant parameter in this integration. So fx0 is simply 1 over x0 minus, I'm sorry, x minus x0. That's what it is. Then we have here the result. A point charge has a potential which is of this form here. It goes with the inverse of the distance, right? Charge divided by distance. Okay? That's the simplest example. Let's calculate the field. Field is the gradient of this potential function. Well, where nabla operates on the coordinates of x, right? So if you go here, nabla of 1 of x minus x0, this is the variable parameter, so this is going to be minus the difference vector divided by the magnitude cubed. Right? So minus nabla is plus that. So the E field is minus nabla. So that's what we have. The E field has the correct dependence on the coordinates. Right? So that's what we have. That's one interesting example. Next, let's take a look at a little more elaborated one. A charged loop, a wire, a loop of wire, you know. So let's see how we represent that density using delta functions, right? This is one way to do it. Let's see how we get to that. So I want to make sure that that rho x prime dv prime integral equals to the charge of this charged line. Let's assume that this charge is Q is linearly, is uniformly distributed over this loop of perimeter 2 pi a length, total length of the circumference 2 pi a. So this is going to be Q, okay? So let's do this calculus separately here. Let's work on the density here. So my density so if I use cylindrical coordinates, right? dv prime equals to r prime dr prime d phi prime dz prime. Integration is on the whole space. Okay. I have some little problem here, but I think it's fixed. So if we do that, if we did triple integral, let's do here from 0 to 2 pi d phi prime, from 0 to infinity, right? R prime dr prime, from minus infinity to infinity dz prime, density function that I have to determine, okay. Notice that the loop is located at r prime equals to a, right? This is going to be q. So this is 2 pi, okay. So so I have an integral from 0 to infinity. This is going to be a function of r prime, right? Let's say that rho x prime. So I'm separating 2 pi here. It's going to be a function of r prime times a function of z prime. So we're going to have f r prime dr prime integration from minus infinity plus infinity of dz prime g of z prime equals to q divided by 2 pi, right? That's the result of this integral here. Now let's say, I mean, the loop is located at z prime equals 0. So this means that gz prime equals to delta of z prime minus 0. I don't have to put that. And this one here, the loop is at r prime equals a. So we have a delta function here, f r prime equals to delta r prime, and I have to have a r prime down here. I'm sorry. R prime minus a divided by r prime. I can use r prime or the value of r prime at which is a, but I can use like this. I'm going to make it different than the class notes. So that's fr prime, okay? That's g. So the density is given by q divided by 2 pi. I forgot to put here, right? So that's the density. F times g. So it's going to be 2 pi r prime delta r prime minus a delta z prime. That's our delta function that we have to use in calculating the potential function. Okay? That can also mean, because this function only exists at r prime equals a, this is the same thing as rho x prime equals to q divided by 2 pi a delta r prime minus a delta z prime. In practice, it's the same thing, because this only occurs at r prime equals a. So let's plug the density, right? So I have q divided by 2 pi. I already put the a here, right? 2 pi a. The z integration is here. This is the r part of the integration, and the phi part of the integration. So this is the location. I mean, I'm calculating at point x equals coordinate z equals z a z. Okay? So that's x. And x prime, well, in fact, let's do it like this. I mean, the correct expression for r prime, I mean, x prime, in fact, I mean, let's do the calculation very formally, okay? I'm going to put this thing here. I'm going to put some, separate this to show you how to do the formal calculation here. Let me copy this and go here, because exactly it's like this. Let's do this here, okay? I'm not going to use that. I mean, x prime, in fact, is a vector in 3D space. X prime equals to r prime a r prime. That's the complete expression for x prime, because we are assuming that the volume is at 3D space. We are picking up a contribution of dv prime, which is at point x prime, and I'm calculating the effect at z equals x equals z, right? So x prime is r prime ar prime plus z prime az. So this integral here is integral from 0 to 2 pi So we have one term which is z minus z prime az plus r prime ar prime. Okay. Even though, sorry. Yeah, that's right. ar prime. Notice that even though this versor here depends on phi prime, which is the variable integration, this magnitude of this vector is constant. This magnitude equals to the dot product of the vector with itself, which is r prime square plus z prime minus z square root square, right? So this is a constant, doesn't depend on phi prime. So the result is 2 pi divided by r square plus, let's put it like this, 2½ right? So I'm going to put this 2 pi here. We're going to cancel this with this. It's going to be 2, right? I'm going to just use the same thing. So I'm going to have here q and here, so this one here at this moment is 2 pi r prime, okay? That's the correct expression. So it is already going to cancel that here, right? But let's just leave it as that. So this one is out. Let's erase this thing here. So the result was, I'm going to put in red so you can see something that we did. 1 over r prime square plus z prime minus z square 2½ This 2 pi, in fact, there's no 2 pi anymore, okay? That's what they have. The next integral is in r. Now notice that I can cancel this r prime here with that one. And this integral is easy to calculate. It's just, I mean, the integral is this function at r prime equals to a. So the result is going to be 1 over a square plus z prime minus z square 2½ Okay, so let's erase that. Just remove this thing here. I mean the integral as a whole, right? Just remove that and put this thing here in place. Now erase this thing here. So the final integral is integral of a function of z prime, which is right there, delta of z prime. So it's going to be the value of the function, which is this one, at z prime equals 0. So this whole thing here is going to result in a value, I'm going to write here, 1 over a square z prime equals 0 plus, I'm going to write the other way. Sorry, like this. Z square plus a square 2 1/2. Okay? So that's this integral here can be replaced by this thing here. right? So let's remove everything else from the calculation. So that's the result, right? I think I forgot something there. There's an A there, is that right? See if I didn't miss anything here. No, I think the class notes. Yeah, there's some typos here in the class notes. I think. Yeah, I think there's some typo there, right? That's I mean the thing you see in the screen right now is the correct expression. This one here. So let's go to the notes and take a look here, right? So that's very confusing here, but oh yeah, this is correct. Okay. So this is correct. I mean, this thing cancels that R prime there. So that's the result we have. I just showed you. And this z squared plus a squared, which is this term here, is simply this distance b, right? This is a. This is a rectangular triangle. I'm sorry, z. So b equals to a square plus z square root square. That's what this is. So in fact, the potential is like we had the charge at a distance b concentrated at any point, right? Any point. That's the charge of the loop. You can calculate the field if you want, but notice that we only calculate the potential on the z-axis. We didn't calculate around. We are going to have tools to calculate around in a couple of lectures. We're going to do that, but now we only calculate the potential on point of coordinates z, right? The z-axis. So you see that we know that due to the, all the charges have the same signal, same sign around the loop. So all of them produce field, right? Which is radial, like this. And we know that by symmetry, the resulting field is going to be on the z-axis. So on the z-axis, the E field points parallel to the z-axis, right? So on z-axis, E equals to E of z az. That's only true because the charge is uniformly distributed. Other distribution would not give that result, okay? We could have a field that's orthogonal to the z-axis, for instance, depending on the distribution. We might have charges that are separated, positive on one side, negative on the other side, could have a resulting field that is orthogonal to the z-axis. That's not the case here. So we know that the E field is along the z-axis. So in this case, so the z component of the field is the gradient along, right? Is the gradient component along the z-axis. So this is nothing less than minus the potential on the z-axis only depends on z, is minus d phi dz. So I can calculate the derivative of that function, okay? So we have phi equals to q over 4 pi epsilon 0 z squared plus a squared to 1/2 So phi dz, you can calculate it, right? It's minus q divided by 4 pi epsilon 0. The derivative here is going to be z over, the minus is already, because the derivative of z squared plus a squared to minus 1/2 equals to minus 1/2 times 2z times z squared plus a squared to 3/2. So the minus sign is right there. So that's what we have for the field. So let's just complete here. The E field equals to, this minus with the minus gives plus, right? So it equals to q over 4 pi epsilon 0 z over z squared plus a squared to 3/2 az, right? So Ez is larger than 0 on the positive axis, and Ez is less than 0 on the negative axis. Ez equals 0 at the origin, right? So I have a loop, right? At this point, the E field points upwards. 0 here, at this point, points downwards. Field is away, right, from this thing here. Okay? Let's go to the next example. And I'm going to show you now how you can obtain the behavior of potential functions that might have a singularity if your charge distribution is infinitely large. Okay, but even if there is this singularity, you can determine the behavior of the potential. I mean, how it depends on coordinates. And from that you can determine the field too. Okay, I'm going to show you this with two examples, I think. Yeah, let's do this one. And I'm also going to emphasize the use of delta functions once again, okay? Let's do this charged straight line, a rectilinear straight line, but has a finite length, like so, okay? We have already our coordinate system drawn here. Let's see the important points here. We have the total length is this line of charge here, right? I'm just going to calculate the potential on the plane that is divides the line of charge in 2 halves. Okay. So, for instance, at this point, I'm going to use something smaller here. Something like this. Maybe like this. At this point here, okay, I mean, if you go through the tip, I think, yeah, we have a maximum angle, which is L over 2. The tangent of this angle is L over 2 divided by R. Okay, and at the lower portion, I mean, this angle is that the same one as that one with a minus sign. Can do that. Okay, so just to show you some important things. So I want to calculate. Sorry, use other thing here. That one. I want to calculate x prime. Sorry, let me just decrease here. Okay, I want to calculate the potential on the plane at the point x prime equals RAR. Okay, again, I'm going to make a more general density function here. Okay, So look, when we use the Dirac delta function, the x prime, which is location of the volume, is not exactly on the line charge, okay? It's the point in space. So let's do it. So you see, once again, we have to determine the charge density using delta functions. So the integration, in this case, the charge has a finite length, okay? So integration in the whole space equals to the charge, which is, in this case, well, the charge is assumed to have a density lambda. Okay, so it's going to be lambda times the length, the total length. If you see the length here is L, the sum of those two halves, lambda L. Lambda is the density, the line density of charge, which is Coulomb per meter, right? So we are going to use cylindrical coordinates. Integral from minus infinity to plus infinity of dz prime. But that in practice is going to be from minus L over 2, right? To L over 2 of dz prime. Times integral, I'm using cylindrical coordinates, 0 to 2 pi d phi prime. Times integral from 0 to infinity of r prime dr prime. So I'm going to use a function of r prime equals to lambda L, right? So what we have here, well, this is L, right? This is 2 pi. So the delta function has to be, is going to have a singularity at r equals 0. So we're going to use, so integral from 0 to infinity r prime dr prime f r prime equals to lambda L. So L cancels out. So we have integral equals to lambda over 2 pi. Now we have to have something here that cancels this r prime. So we have to have a delta function minus 0, right? At the z-axis divided by r prime. So we have already the definition of fr prime, right? So it's delta r prime over r prime. And our density, what is our density? What happened to our density? Well, our density is going to be, our density is going to be rho x prime equals to lambda over 2 pi r prime delta r prime. That's the density. Okay. If you integrate in the whole space, you get the charge, which is lambda times L. So that's the density, right? So so that's one part of the problem. So let's then calculate the potential of this charge distribution at point x equals RAR. Let's write down the expression. So potential equals to integral in the whole space, not in the whole space, in the part that contains the distribution throughout a length L, okay? So it's going to be integral from minus L over 2 to L over 2 dz prime, right? Integral from 0 to 2 pi d phi prime, integral from 0 to infinity, so the whole space, r prime dr prime. Then we have the density function, which is lambda over 2 pi delta r prime. So that's everything here is the density. Okay, so here we have already written rho and dv prime. So we only need to write down 1 over x minus x prime. X equals to RAR. What is x prime? X prime equals to R prime AR prime. Notice that those versus are different, right? AR is fixed, AR prime is variable, plus Z prime AZ. Okay? So magnitude of x minus x prime equals to magnitude of R AR plus R prime AR prime, minus R prime AR prime minus Z prime AZ. Okay, those vectors are orthogonal. Okay, so let's call this vector a vector V. Okay, so this magnitude equals to magnitude of V square plus Z prime square, 2.5. Okay, so that's what we have. So when you do the integral, we are going to have integral from minus L over 2 to L over 2 dz prime, integral in R, in phi, from 0 to 2 pi d phi prime. Then we have this integral here, so 0 to infinity r prime, dr prime. I forgot the 4 pi epsilon 0 somewhere, right? So there's 1 over 4 pi epsilon 0 here. So let me put here, okay? 4 pi epsilon 0. You're going to have lambda over 2 pi. Then we have, I think I'm missing some r, I'm missing some r prime here. I didn't put that. Okay. So it's going to be 1 over v square plus z prime square to 1/2. Well, this r prime cancels. So this is only going to happen at r prime equals 0. At r prime equals 0, v becomes RAR, and v square plus z prime square becomes r square plus z prime square. So this integral here is lambda over 2 pi 1 over r square plus z prime square to 1/2. Okay, now it becomes easier, right? So this is going to be 2 pi cancels with that. So we end up with the integral of this function, this z. Okay, that's what we have. So in fact, just to show, just can go straight here now, just to show where we got. So that's the final integral that we have. Have this factor here, then this integration. That one I'll leave it to you, okay? But the trick is to make the substitution z prime equals to r tangent of alpha. Okay, so z prime. Let me do that a separate drawing here. So we have here, right, r, so a point z prime, then we have alpha is this variable angle that goes to a maximum value alpha plus, which I showed at the beginning, right? Is when this length is L over 2. So tangent of alpha equals z prime over r. So I make that substitution, z prime equals r tangent of alpha, dz prime equals r secant square of alpha, the alpha, right? So the integral, I can do it here, minus L over 2 to L over 2 dz prime equals to, so that's dz prime r square. If I put r square as a factor here, it's going to be r square 1 plus z prime square over r square, which equals to r square 1 plus tangent square of alpha. In fact, I have to use the tangent in English here. I'm using tangent in Portuguese. So this tangent, I think in the notes also, tangent of alpha. That's the English way of referring to tangents. This sec square of alpha, right? Now, notice that alpha, being either positive or negative, the secant function, equals, is 1 over cosine of alpha, right? It's positive if alpha secant of plus or minus alpha equals to secant of alpha. That's the property here. So you don't, when we extract the square root here, I can, without any problem, just do r sec alpha, right? Because the root square of sec square is sec. So this z prime is sec square. So we're going to have that integral that many of you minus alpha plus to alpha plus of sec of alpha, the alpha. That's one of those tricky integrals that you might have, I'm sure you have seen before. This alpha plus is the maximum value of the angle at the tip of the line of chart. This is can be done by multiplying and dividing by sec alpha plus tangent of alpha. Okay, if you multiply and divide by this factor, you're going to have integral sec alpha square plus sec alpha tangent alpha, the alpha, this integral here, sec square, is tangent, and this integral here is sec alpha. Okay. Sorry, I forgot just to put the denominator here. Sorry about that. I just did too quickly. So derivative of sec alpha is sec alpha tangent of alpha. Derivative of tangent alpha is sec square. So this is the logarithm of sec alpha plus tangent of alpha between limits minus alpha plus to alpha plus, which is going to be the ratio, right? Sec alpha plus tangent of alpha plus. Then you go sec of minus alpha plus, which is sec of alpha plus. Tangent of minus alpha plus is minus tangent of alpha plus. So this is going to be minus tangent of alpha plus. So recall that those things, right, as I mentioned to you, sec of alpha plus, or the tangent of alpha plus, is L over 2 divided by R. So we can express back everything in terms of the parameters. Length of the wire and distance, radial distance. Okay. So we can erase everything here so we can see it clearly. Okay, there's nothing else. So it's right here, the relationship, right? So we have that. So when you calculate and express everything in terms of the distance r and the length, you get this expression, right? Already worked out a little bit. So that's the exact, that's the potential at plane z equals 0, right? So one important thing is when you have an infinitely long wire, what is the result that we get, right? Well, then we have to be careful when doing approximations here, because we might blow up the potential function. We don't want to do that. We want to make sure that we have a very large length, but not infinite length, but large. Very large relative to the distance in the plane, let's say, okay? So I want to make a very long wire. So I'm here in the plane. In fact, I want to calculate close to the, let me just increase a little bit here. That's the plane, right? I want to be on a distance r, which is much less than the length of the wire. In other words, I want to make, that's the approximation. A long wire is the same thing as calculating the potential very close to the wire, right? In practice, it is as if the wire was an infinite wire. So what happens? As r is much less than L, right? I can neglect this term here, okay? On the other hand, I cannot neglect this term here, because if I do that, it's going to be 1 minus 1, which is 0. Then we have a 0 on the denominator. We don't want to do that. Here we have to make a careful approximation, okay? But here I can surely do a very good approximation, just neglecting this factor here. So in the numerator, we are going to use that approximation. In the denominator, we are going to use a Taylor, approximation to first order. So let's look here. Let me just clean up a little things here. So there's things too many sketches. Okay, I think we have some space there. So look at that, we have this function here, right? Small value of this parameter. So we have 1 plus epsilon. Epsilon is a small number, 2 1/2. Is that so? Yeah. That's the function we have here. So this to first order is 1 plus epsilon over 2, right? The first derivative is 1/2 times the function at epsilon equals 0. It's going to give that approximation. So that's why we have, when you have this term, minus 1, when you do this minus 1, this is going to be minus 1 equals to epsilon over 2. Epsilon is that ratio 2r over L, right? So you're going to have that result. So the potential is going to have this behavior here, logarithm 2, there's 1/2 here, this factor there, then you obtain this result. Okay, so we have this result here. You can separate log of L. So the potential in the plane z equals 0. So in the middle of a long straight line of charge equals lambda over 2 pi epsilon 0 log, natural log, what is it? Natural log of L over R, right? So equals to lambda log of L minus lambda over 2 pi epsilon 0 log of R. So this is a number. If L goes to infinity, it's going to be an infinity number. If it doesn't go, if it's very large, it's going to be a number, right? So as the larger is this parameter, the potential is going to be more insensitive to change in this one because this dominates. Okay, so I can say that the potential is a constant value A minus lambda over 2 pi epsilon 0 log of R. Right? So that's how the potential is. We can make a plot of that. Okay, make a plot of the potential. Can make like this. Let's look at the other one. R is more than L. So the potential is positive. Minus log over L. So it's minus log. So log is like this. It's something like this. It's something like this, okay? So the log function is something like this. The minus log function is something like that. Plus a large number is going to be something that's shifted like this. Okay? That's the way the potential behaves. It's going to go to infinity at r equals 0, right? But that's the behavior. And from this behavior, I can determine the E field in the radial distance. I mean the E field component looking at the plane. Okay, now let's look at the plane. The wire is right in the center. I'm determining the potential, how it changes with R. I'm saying that it changes with the minus log, natural log of R, right? So I can calculate the E field component in the plane. The radial component, in fact, ER equals to minus d phi dr, right? Which is minus, if you look at the expression, derivative of log function is 1 over R, there is minus there. So that's the behavior we get. Sorry, plus, right? Because there's a minus sign with this minus sign here, gives a plus. So the E field is the E field that we calculated before with Gauss's law, right? If we make an infinitely long wire, that's the exact result we get. The E field equals to lambda divided by 2 pi epsilon 0 r a r. Okay? There's some couple of additional examples here. I I'm going to just going to outline this one. I'm not going to work it out. You do it, okay? You can define your delta functions, but just to express the result, I'm going to just to show some landmarks in this example. You have a charged disk. That's the same thing. I can calculate the potential on the z-axis, okay, of the charged disk, uniformly charged disk. Then I can expand this to make it very large, so as to become a large flat plane, right? Flat surface. A large plane at z equals 0. Then I have the behavior of the potential on the axis that is in the center of the plane. Then I can calculate the field and see how what happens as the plane goes to infinity, right? Can do that. Again, this is the density function. I'm just going to show you now the result. You work it out. This is the density function that represents the surface density, okay, which is a constant density on a disk of radius r, sorry, okay? So this is the way to calculate this. You do that, right? So again, always remembering, right? The V prime is going to be a volume. We are going to use cylindrical coordinates once again. I'm going to calculate the potential on the z-axis, right? So x is defined, z, x prime is the position vector in cylindrical coordinates, rar plus z prime az, right? So we have that easily, this magnitude that appears in the expression, z prime minus z square plus r prime square. Then you can do the calculations, right? You can integrate the whole space. The delta function is going to pick up at z prime equals 0. So we have a very simple integral to be calculated here. But now, this one here. So we have this factor here. The derivative of this factor is the one that is on the numerator. It's easy to calculate. But you have to be careful when extracting. I'm going to do this calculation just to show the important detail here, which you have to be always careful when you calculate the integrals. Before you calculate the integral, look at the integrand, okay? This is a function which is always positive, okay? The result must be a positive result. That's the most important thing about doing those calculations. You cannot have an integral in which a function might become negative. The function that is the result of this integration must always, you have to guarantee that it's positive. So that's the idea, okay? So let's do it here, this calculation here. So that's the calculation we have. Is integral from 0 to a, okay, on the surface of the disk, but there's only one integral we have to calculate. So it's r prime square plus z square, because z prime has already picked up at z prime equals 0. So this is 1/2. So you can call this u du over 2 equals to r prime dr prime. So limits r prime equals 0, u equals to z square, right? R prime equals a, u equals to a square plus z square. So we have a change of variables here. This integral becomes integral from r prime equals z square to a square plus z square. So we have 1 over u to 1/2 du over 2, which equals to 1/2 of integral of 1 minus half du from z square to a square plus z square, right? So it's going to be 1/2. Is this right? Yes, 1/2. So this integral is 1 to the 1/2 from the two limits, z square, a square plus z square. So it's going to be, did I miss something here? Oh, sorry. This is 1 u1 to 1/2. Sorry. Because the derivative is 1/2 times 2 equals 1. So this is going to be a square plus z square to 1/2. And here I'm going to do like this, minus z square to 1/2. Remember that z might be positive or negative, right? So we have to be careful when extracting the square root. This is always a positive square root. On the other hand, I have to make sure that the square root is always positive. So this is going to be minus magnitude of z. Okay? So that's how you do it. When you extract the square root of a positive number, you have to guarantee that the result is a positive number. And you cannot change the sign, because if you just do that equals to z, it might be negative or positive, right? That's not correct. I mean, we cannot change the sign of something that doesn't change sign. So that's the important detail here. So that's why we have this result. Okay. Just fix here. Magnitude of z. So that's how the potential behaves. Notice that if I increase the radius of the disk very much, I can go limit as a goes to infinity. This goes to infinity, this part here, right? This part here. Okay? So let's see what happens. If we have a very large disk, infinite flat surface, a plane. So I can simply say that a square plus z square approximately equals to a. So the potential behaves like this. There's a part that goes very high, right? And there's a magnitude function here. Let's plot the function, okay? Potential function of on the z-axis is a constant, right? So the potential has at z equals 0 is going to be a large value, something like, I'm going to just make like this, which is rho SA over 2 epsilon 0. Then have the magnitude function, something like this. That's the potential as a function of z. Okay. So that's how it is. So this is going to be very large because of A, right? So in fact, in practice, you could see something like this, right? Very large. But what is important is how the potential varies with z. That varies linearly on either side of the plane, of the surface, right? So you can determine, by doing this, you can determine what is the field of an infinitely large plane. Well, calculate the E field on the z-axis. The derivative of the magnitude function is constant, right? Or 1 or minus 1, depending on where you are. Okay, z over magnitude of z, or vice versa, magnitude of z over z. So the field is going to be, using the gradient function, you determine the field of a large surface, charged, uniformly charged. It's going to be always constant, right? I'll put here the plane. So the field is always pointing. Let's say that rho s is larger than 0. The E field is uniform, like this, for z larger than 0. And it's like that. That's because it has those charges on the surface. Let's put positive charge here, right? Assemble those charges on a plane, and we're going to have a constant field that even far away from the distribution, the field is always the same. It's rho s over 2 epsilon 0. That's the only, that's an idealization in which the field is constant even at infinity, right? But that's an approximation. I mean, we don't have infinite distributions of charge. We have localized distributions, but the field has to decrease as you move away from the source. Okay. Let's move on. Let's talk about energy now, right? We have an interpretation in which the potential is directly related to the energy of a point charge on a point in which you have a field. So let's do the calculation of this energy. Let's call it potential energy. In vacuum, right? Because the only thing that we have are charges and vacuum. We don't have any other type of, we don't have insulating atom, insulating materials, you know, uncharged, non-ionized atoms and molecules. We don't have that. We're going to use that. I mean, we're going to introduce that, but we don't have that yet. So if you do the process of bringing, this is, we just spoke about that in the beginning of the class, right? When you bring, we are just reviewing here. When you bring a point charge to a point P, right? You have, assuming that the energy at infinity, that the potential at infinity is reference is 0. So, I mean, knowing the energy at point P is a way of knowing the potential. So, the potential, as we showed, is the energy of the charge divided by the charge, right? I also show that the field is conservative, 0 circulation, right? So, the question is, what would be the energy of putting together n charges in a system and leaving those n charges, you know, static in those final positions? So the way to do this is to bring one by one. Okay, so if you bring the first charge to your system, you're going to assemble n charges. If I bring the first charge to a point without previous charges there, there's no interaction with no other charges, right? So energy equals 0. Just to bring the I equals 1 charge. So W is the energy of the system for only one charge equals to 0. Now, if I bring the next charge, Q2, close to Q1. Q1, the first charge is already there. So this is Q1. Then I bring another charge, Q2. The system has now an energy, which is the energy of this charge here in the presence of this charge. Okay? So that would be the energy of the system now, W2, right? W2 equals to what? Equals to, I'm going to write like this, Q2 times the potential that one exerts on 2. Phi 1, 2. Okay? So that would be Q2 times the potential of a point charge is the charge location is x1, location of second charge is x2. So it's going to be Q2 times Q1 over 4 pi epsilon 0 x2 minus x1. Right? So energy to have two charges, right? Now, if I go now to the third charge, the energy is going to be the charge Q3 times the potential at the location of the charge 3. Well, the potential now is the sum so the new energy that the new energy that I have to add is the energy of Q3 in the presence of the previous charges, right? So I bring Q3 here, position X3. So the energy to add this third charge is going to be W3 equals to Q3, right? Potential at position 3, which equals to Q3. Then you have charge 2 on position 3 and charge 1 on position 3. The potential is the sum of the two potentials. Plus Q2, right? X3 minus X2. That's what we have now. Okay, Q3 times Q1, Q3 times Q2. So the energy is going to be Q3 times the sum of the indices less than 3, from j equals 1 to j equals 2, of Kj x3 minus xj, right? So to add the final charge Wi, to add the ith charge, what I have, I just multiply Qi by the sum of terms like this with the index j less than I. So j goes from 1 to I minus 1. Okay? So that's the energy to add Wi, right? So the total energy is the sum of these additions. Okay? W equals to the sum from W equals, so from I equals to 1 to n of Wi, with W1 equals to 0 because it's the first charge. Right? So it's going to be, every time, for the ith charge, you have to make a summation of j is smaller than I. So that's what you have. The energy is going to be this expression, simple expression here. The total energy, you keep adding and calculate with the ith addition. You have a Wi energy addition. You sum all these additions to get the total energy, right? This double sum can be made with different indices, if you make a 1/2 here, okay? Put 1/2, you can show that you can, if you have a conditional sum like this, I is freely variable from 1 to n, but j is constrained to be smaller than I, is the same thing as, because you always have terms in which one factor is larger than the other, right? In this one here, we have 2 times the same factor. Q1, Q2, Q2, Q1. You have to divide by 2 because they give the same contribution. Because this thing here doesn't change. So that's the energy of a system of any charges. Okay? Well, if you have a continuous charge distribution, or continuous charge distributions, I mean the ith charge is a density times the volume around the ith charge. Let's say ith charge is at x vector, j charge is at x prime vector, right? So then you'd have the summation becomes an integral, right? So we have a double volume integral here, dv prime. That's what you would have. So this is this thing here is dq, and this thing here is dq prime, right? So you can factor out this rho dv outside. Then you have one factor which you can identify as the potential at point x due to the charge distribution rho x prime. So that's what you have. For a charge distribution, you have this expression for the energy. So the charge distribution produces a potential function within it or outside it, given by the function phi of x. So this integral gives the energy of the charge distribution. Okay. This is called the point of view of the field source, because explicitly the term that appears in the integral is the charge density here. Okay? In a couple of minutes, we're going to show this expression in the point of view of the field itself, in which charge doesn't appear in the expression. Okay? All right. Let's move to the final part of the lecture today. We're going to now, we have all the formulation that is required for establishing Maxwell's equations for the particular case of electrostatics in vacuum. We have one first property here, which is the flux of the vector d. Just recalling, the vector d is a very special particular case definition of the flux density vector, which is in vacuum is equals to epsilon 0 e. We use that in this first equation in Gauss's law, okay, because we eliminate the epsilon 0 factor in this thing here, right? Otherwise, if we use the E field here, you'd have an epsilon 0 in this term here. So we avoid using epsilon 0 by defining a particular definition now. We're going to show that this equation is going to remain the same even in material media. But for now, let's accept that. So we have the first integral equation is Gauss's law. The flux outwards, a closed volume, through a surface, calculated across the surface, equals the enclosed charge. The second integral relation is that the field is conservative. Okay? Now, those relations, according to our theorem, our theorems, vector analysis theorems derived in the first part of the first classes, first lectures. Well, let's just quickly do here. Gauss's theorem. We have Gauss's law and Gauss's theorem, which says that, specifies that flux of a vector equals to the volume integral. I mean, this enclosed surface, enclosing surface sigma, encloses the volume V, equals to dV divergent of A. So if we have that equation, right, the sigma flux equals to integral of rho dV. So here we're going to use this property, Gauss's theorem. So it's volume integral divergent of D equals to that. So these two equations can be combined into a single equation. And this is valid whenever is V, whatever V you can use. In particular, if you make V a differential volume, this integral is simply the product of delta V times is equals 0, whatever value of delta V you use. If it's very small, okay, pick a differential volume. So we can show that this is non-zero, so it means that this thing has to be 0. So that's the first differential equation that we get. Differential form of Gauss's law, right? Divergent of D is a detector of source of field source, right? So if there's a density here, the positive density means that we have field lines coming out. Those field lines will be represented by D or E. D and E are the, are two versions of the same effect, which is the electric effect, right? So this is a positive density, or you can have lines of field lines converging to the points. We have a negative density. So that's our interpretation, right? Divergence of D is a detector of the field source, which is the charge density itself. Second property is this one, right? Circulation of V equals 0. Well, we have two ways of doing this. Stokes' theorem states that circulation of a field equals to the curl of the field on the surface that encloses the path. I mean, the surface that's open surface enclosed by C have the curl of A. In our case, we have circulation of E field equals to curl of A. And again, I'm going to make a differential. I'm going to make here a differential area, delta sigma. That's the vector. So if sigma goes to a very small area, and this is equal to 0, right? So this becomes the dot product between the area itself, which is like this, times curl of E. Sorry, this is Z here, right? Equals 0. And this is independently of the choice of delta sigma. This dot product can be 0 if the vectors are orthogonal. But it means that whatever delta sigma I choose, the dot product is 0. There's only one possibility, which is the curl of E equals 0. Okay, this is independent of delta sigma. So there's only one possibility, curl of E equals 0. That's the second integral, right? I mean, we knew that. I mean, any conservative field, which is obtained from the gradient of a scalar function, which is the E field, is irrotational. That's the property, right? Okay? So that's what we have for our Maxwell's equations in vacuum. We have two integral relations, right? Two integral relations, or equivalently, we have two differential equations. We're going to see, of course, these are particular expressions for the more general Maxwell's equations for the electromagnetic field, for the dynamic electromagnetic field. We're going to see that this one has to be changed, but this one will remain unchanged with the proper definition of D, right? We're going to see that that remains unchanged, but this one will have to be changed when you have dynamic fields. So we have already one correct Maxwell's equation that is going to be valid even for dynamic fields. Very well. Now we are going to derive the energy from the point of view of the field itself. Okay, so we're going to make a change of variables in the integral expression for the energy to express it in terms of field quantities. This is the original expression. Now we have Maxwell's equations for electrostatics in vacuum, in which rho is the divergence of D, right? So we have here this integral here. Now this is one term of the chain rule of the nabla, the divergence of a vector times a function. Divergence of a function times a vector. Function divergence of vector plus vector dot product with the gradient of the function. The function here is the phi, in our case. And the A vector is the D vector. So let's look. So we're going to have phi divergence of D. So this phi times D, right? Plus D dot gradient of phi, right? So this is the rho function that we have. So we are transforming rho phi equals to this term here, divergence of rho, divergence of phi times D minus D dot nabla of phi, which is plus D dot E, because E equals to minus the nabla of that. So that's what we have. I mean, the integral that appears to calculate the energy can be separated in those two terms here. Okay? So that's what we got right there. Divergent phi times D minus I didn't put the E field yet, but you see that we have minus sign minus nabla of phi. This is, I mean, this volume integral here becomes this term here. On the other hand, this integral, by Gauss's theorem, this is the flux of this vector across the surface that binds the volume of integration volume, is right there. Right? So I have the surface elements, potential function, and D. Well, what is the size of the surface? Well, the volume is the entire volume whenever we have charges, right? We have here a charge distribution, not there, let me put here, which occupies a finite volume. My integration can be made in the entire volume. So I'm integrating across the entire volume, right? I mean, the whole space. And let's go, I mean, when you do that, you go very far away with a surface that has a radius r. This is a surface. The normal is AR. This size goes to infinity, and as a result, the charge becomes a point charge at the center of the volume, Q. The whole charge distribution can be considered on a point because you are so far away. So you pick up the whole everything, right? So what happens? Potential goes with 1 over r for the point charge. Flux density goes with 1 over r squared, right? And the surface increases with r squared. Okay? So the whole thing, so recall that this thing, this r squared, the omega, right? AR. So that's why I have r squared with r squared. So this is going to be 4 pi over r in the limit. In fact, it's going to be something like this. The integral is going to be limit as r goes to infinity, unless of some constant is going to be the angle, solid angle over r, which is equals to 0. So no such a term is going to contribute to the energy, and the energy can be written in this form. Which is the volume density of energy density. Energy density being this parameter here, 1/2 of d dot E, which is measured as joules per cubic meter. It's as if the space which is fulfilled with field had an energy which depends on the square, let's say, because dE is the square of the field. So high field intensities are related to high energy density regions. With the point charge there is going to be repelled or pulled very strongly, right? And low field regions, low field intensity regions are points with low energy densities. So that's what we have. So that's why it's called, I mean, the energy in the point of view. So the final expression is something like this. So now the energy, electrical energy, is 1/2 of dE, dV, right? So this is the point of view of the field. There is no charge in the integral. Integral is made in the whole space. Wherever you have a field, you have to pick up that contribution. Otherwise, you are losing some parts of the energy term. Okay. Finally, I'm going to talk about boundary condition. I'm going to explore that in further, right? I'm just going to establish the equations. And we are going to use it further. As we use it, it's going to be easier for us to understand better the concept. But I mean, boundary conditions, they are the results of the integral relations, Maxwell's equation in the integral form. So we have flux outside volume across the surface that bounds, that limit, that encloses that volume, is the enclosed charge. So if we make a boundary between two regions, 1 and 2, those regions might be different, for instance, because medium 1 might be a conductor, right? Medium 2 might be vacuum. Medium 1 might be a dielectric, medium 2 another type of dielectric. So I have two different regions which are separated at the interface, and the normal at the interface that always points from 1 to 2 is n. So we build here a cylinder of a small height, delta H, and a differential area, delta sigma. Okay, so we calculate the flux out to the outside of the cylinder, as the height goes to 0. So if we do that, the charge density, the charge that is enclosed by the cylinder, if we have some surface charge density, I mean that integration is going to pick up only the surface contribution. So that's the result that you obtain. The flux on the surface of the cylinder is going to be 0 across the lateral surface, because delta H goes to 0. The area goes to 0 as delta H goes to 0. So we're only going to have a contribution on the top surface, top disk of the cylinder, and the lower disk of the cylinder here. So, and you see that the area of the disk is delta sigma. So we're going to have from the medium 2, you're going to have n d2 times delta sigma. And the flux going outside is minus on the medium 1, because I'm assuming that n is inward, the volume. So there's a contribution, and d1 delta sigma times n. So when you equal those things, you cancel this delta sigma here with that one. So we have the first boundary condition that comes out from Gauss's law. Okay? There's a discontinuity in the normal component of the flux density vector if you have a surface charge density. Okay? If you don't have a surface charge density on the surface, you don't have a charge density on the surface, then the normal component of the D field is continuous. Okay? Second property, so if I make a plot, just to show you, just to illustrate, if you make a plot of the field, D field, right? So let's say this is the normal component. We are looking at the normal component of D. This is the boundary between the two regions, right? So it means that we have two different functions, region 1 and region 2. So function 1 might be something like that, right? Well, if there is a surface charge density, the normal component at the boundary, there's going to be a discontinuity, let's say, like this. In this case, the normal component increases a little bit. There's a positive discontinuity, because in this case, rho s is larger than 0, right? Otherwise, you can have another case. If rho s is negative, your function would be something like this. So you have a drop, right? That's when rho s is less than 0. So there's a discontinuity So if we have the third case is when rho s equals 0, then we have something like this. The n is continuous. That's rho s equals 0, right? Finally, second equation. Now I'm going to express the integral equation, Maxwell's equation, as this very simple relation here, right? Well, if curl of E equals 0, it means that the volume integral of curl of E is also equal to 0. And recall that we had that theorem relating the volume integral of curl of E, which is the dual of the divergent of E in the volume, which gives surface integral of the sigma cross product with E equals 0. Okay. Then we make also a small cylinder and calculate the integral on the surface. You see that again on the lateral surface, the surface contribution goes to 0 as the height goes to 0. So the only remaining contributions are those from the top disk, delta sigma times n, cross product with E on the upper side, and the other contribution is from the lower disk. So what you have is something like that. And you make the height small, right? The limits. So we know the lateral contribution. We have only contribution from top and lower part. So we are connecting the fields on the interface. So the results that we get, we're going to have here, in fact, is this delta sigma times n equals 0, right? So delta sigma, you can remove it. So that's what we have. That's the boundary condition on the E field, which is this one. N cross product with the difference between vectors on the two sides equals 0. So that means, let's make it separately here, that the fields have the same tangential component. Let's make a drawing here, okay? So that's the normal. Sorry, make it better here, normal. So let's say that this is a vector AE on the side 2. So if I draw the E field on side 1 starting on this point, it has to end in such a way that the difference is parallel to n. Okay? So the tip of vector 1, E1, has to end something like this. So E2 minus E1 is parallel to n. So this is a real vector definition. I mean, those three vectors are in the same plane, n, E2, and E1. Okay? They are in the same plane. So if E2 minus E1 is truly parallel to n, then you have the cross product n cross E2 minus E1 equals 0 because this difference vector is parallel to n. I mean, parallel vectors have 0 cross product, right? So that's the second boundary condition we get, which is this one. This implies that the tangential component of the field is continuous. Make a plot. That's always true, right? E tangential, coordinates boundary. The E field comes like this. It's always going to have tangential component, which is the same on the two sides. So even though we might have a discontinuity in derivative, but we have a continuous connection of the tangential components. Okay? With this, we conclude this lecture number 5. And we hope to see you next time. Till then, bye-bye.